This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, your professor for this University of Texas at Austin course, and we're at lecture 49, another lecture on lithography. This time we'll introduce some concepts about photoresists and talk more specifically about one type of photoresist called the DNQ Novolak Resist. So let's review what we've already talked about in terms of the tasks of a photoresist. As we've mentioned before, a photoresist has two main tasks: to photo and to resist. Photo means to form an image, and resist means to resist, etch, and implant, so that we can transfer that image into the substrate. Now, these aren't the only tasks for a photoresist. We must be able to coat the resist onto the wafer effectively with good uniformity, with no defects. We must be able to photo and resist. We also must be able to strip the resist off when we're done. We must have good adhesion of the resist to the substrate, etc. So there are more than just these two tasks, but these are the important tasks. And it is hard to find one material, one chemical component that can do all of these things. So we end up dividing up the labor, mixing multiple components together to make our photoresists. First, we have the photoactive compound, PAC or PAC. This is also called a sensitizer. In some materials, it's called a photoacid generator. There are different names for different materials. I'll try to use the generic term sensitizer most of the time. And that is the component that reacts chemically to light. It helps to do the photo piece. Typically, though, these photoactive compounds, these sensitizers, the materials that react with light, aren't very good at etch resistance or implant stopping power. So we tend to use another material, a polymer, resin, that provides the backbone of the material. The majority of the weight of the material is made up of the polymer. It has the temperature capabilities to withstand higher temperatures, has structural integrity, and allows resistance to etching and implant. It's not that we have complete division of labor here, because it's the interaction of the polymer with the sensitizer that allows the photo part to proceed. Then we have a solvent that mixes the two other components together into a liquid so that we can spin coat. We have other materials we might add, some adhesion promoters, maybe leveling agents to improve the uniformity of coating, etc. But these are the main photoresist components. The two main types of photoresists that we're going to talk about, first today we're going to talk about what are called conventional resists, such as the DNQ Novolak resist. These are resists used at the G-line and I-line wavelengths. Remember, G-line is a line of the mercury arc lamp spectrum, and it has a wavelength of 436 nanometers. So that's a visible light, kind of a deep blue color. I-line is into the UV, it's not visible, at 365 nanometers. But today we tend to use 248 and 193 nanometer lithography with excimer lasers, and the modern resists we use at these wavelengths are called chemically amplified resists. Other than a brief introduction, we'll reserve our discussion of chemically amplified resists to a later lecture. Let's talk about three different resist types. I just mentioned two, we'll mention one more. The earliest photoresists that we used in semiconductor manufacturing were cross-linking negative resists. Kodak invented a material called KTFR, Kodak thin film resist. It was based on a synthetic rubber that was a low molecular weight, but mixed into it was something called a cross-linking agent. This was a photosensitive material, molecule that had two ends that were reactive. And so you'd expose it and make one of the ends reactive, and it would react with a polymer molecule. Then the other end could also react with a polymer molecule, causing a cross-linking between those two molecules, increasing the molecular weight. Further cross-links would increase the molecular weight more, and eventually the molecular weight got high enough that the material was no longer soluble in a solvent developer. So the unexposed materials would dissolve away, But the exposed materials would be cross-linked and they would remain behind. That makes it a negative resist. These resists had pretty good etch resistance and excellent adhesion, but they had resolution problems. You really couldn't use these resists below about 2 microns because the unexposed materials, while it would not develop away in the solvent developer, it could absorb developer and swell, and that resulted in a resolution limit on these materials. We used these resists throughout the 60s, but by the 1970s it became obvious that a new class of material was much better. These are the DNQ Novolak resists. That's going to be the subject of most of our discussion today. Here, exposure generates a product and that product changes the solubility of the photoresist. So it's a solubility change, not a molecular weight change. That solubility change caused by differences in chemistry rather than molecular weight. Chemically amplified resists work in a different way. As I said, we'll talk about these in a subsequent lecture, but exposure does not directly affect the solubility or the dissolution rate of the photoresist material. Instead, we need a second reaction during a bake step called the post-exposure bake that causes these materials to change their solubility in developer. Let's hone in on the DNQ Novolak resist and talk about what these are and how they work. First, the DNQ. DNQ stands for diazonaphthoquinone. Well, that's a name only a chemist could love. Diazonaphthoquinone. It's our sensitizer or our photoactive compound or PAC. And while the name is long, if you're a chemist, you get used to these things, that all the different parts of the name have fairly easy to understand meanings. First of all, azo. Azo means nitrogen. So diazo means 2 nitrogens. That's this, 2 nitrogens. Naphtho comes from the root naphthalene, and naphthalene is 2 of these rings, these benzene rings attached to each other. So if I had nothing but 2 of these aromatic rings, none of the other materials connected to it, I would have naphthalene. If I attach this oxygen to the naphthalene rings, I call this oxygen a quinone. I actually don't know why, but that's the historic name for them, a quinone. And so this oxygen attached to these 2 rings is called naphthoquinone, so we have diazonaphthoquinone. The R is a generic label that says something else is attached here. And that something else can vary depending on the resist formulations. It doesn't directly impact the kinetics and the behavior of the exposure reaction for our sensitizer, so we'll ignore it. Often, by the way, this R will be called a ballast molecule, and it will allow us to attach more than one DNQ to the same photoactive compound. As I said, that won't really affect us. We'll focus on the part of the molecule that reacts, which is this part up here with the nitrogens. Mixed with the DNQ is our Novolac resin. Novolac resin is a phenolic resin. Phenolic means this OH group attached to a benzene ring. A benzene ring, 6-membered ring with shared electrons. That's what the circle means. It's an aromatic compound. So there is a phenol compound. And then we connect a bunch of these together to create a chain of phenols groups, phenol molecules called monomers, which form a polymer. Polymer means poly, many, mers, individual units. Monomer is a single individual unit, so this would be one monomer connected to other monomers to create a polymer. The chain length can be short or long. In fact, most photoresists have a mix of short length, maybe 5 or 6 monomers strung together, all the way up to maybe 20. And we'll have a mixture of high and low molecular weight versions of this polymer. This methyl group is attached somewhere on this ring, and because its position can vary, I just generically show it as being attached in the middle of the ring. It's not really attached to the middle. It might be attached to this spot, might be attached to this spot, or this spot, These different spots are named ortho, para, meta positions, and different Novolak resins will have different positions for these methyl groups. Let's look at the chemistry of the DNQ upon exposure to light. Generically, I'll call the concentration of DNQ, I'll call it M, and M reacts with UV light to form some product P. So this is our simple little chemical reaction. But if we look at it in more detail, the DNQ here reacts with exposure to UV light, takes up water, and forms a carboxylic acid. Well, it's actually this double bonds of the nitrogen with the ring that is the light-sensitive material. Azo groups and diazo groups often make up dyes because they're sensitive to light in the visible region. And when we absorb light energy, here we break these bonds, and that's why the nitrogen gas comes off. Then, in its high energy state, it can relax to a lower energy state by opening up the ring. So here's a 6-membered ring. It opens up and forms a 5-membered ring with one of the carbons in the ring coming out and forming carboxylic acid. The mechanism is something called a Wolff rearrangement, very common type of mechanism. Note that water has to be present as well for this reaction to proceed. So you might wonder, where does the water come from? Well, it comes from the atmosphere. Humidity in the air supplies the water, and this is why, in fact, the humidity in the air in our clean room has to be controlled. It's typically set at about 40%. If it drops below about 30%, these photoresists no longer work. There's not enough water to make this reaction proceed. If it gets above about 50%, then our equipment in the clean room begins to rust. So we have a window of acceptable humidities, and we pick about 40% as the humidity level that we want in our clean rooms. Well, this diisonaphthoquinone is sometimes called a dissolution inhibitor. I'll mention why in a moment. And the carboxylic acid is called a dissolution enhancer. But basically, the important thing to note here is that we're changing the solubility of the resist upon exposure. Solubility in what? Well, our developer. What developer should we use? Carboxylic acid is an acid. Think of acetic acid. It's a weak acid, but an acid nonetheless. It likes water. It will dissolve in water, and it will especially dissolve in aqueous base. So we'll use aqueous base as our developer. It will like to preferentially dissolve away the carboxylic acid, the exposed resist material. The diisonaphthoquinone, however, is not soluble in our developer. Naphthalene, the underlying component here, is in fact a greasy kind of a molecule. It doesn't like water. The common name for naphthalene, by the way, mothballs. Mothballs are greasy, slimy kinds of materials that are not soluble in water, but when it turns into this carboxylic acid, it becomes soluble in our aqueous base. As such, exposure creates a solubility differential between exposed and unexposed materials. But it's more than just that. It's not just that the DNQ is changing from being insoluble to soluble. The DNQ interacts through hydrogen bonding with the Novolak resin to change the solubility of the Novolak resin itself. We can see that in something called the Meyerhofer plot. Here I show the development rate, the dissolution rate of the resist material, as a function of how much DNQ sensitizer I've added. So here I call it the inhibitor concentration, but that's just another name for the sensitizer concentration in this context. When the inhibitor concentration is 0, I have pure Novolak resin. So I coat a film of pure Novolak resin onto the wafer, I put it into a developer, and I watch how fast the thickness of the Novolak resin goes down. Eventually it all disappears and washes away. But the rate at which the thickness decreases is called the development rate, and it's measured in nanometers per second. And so here I have a resin that dissolves at a rate of about 25 nanometers per second. But if I start adding DNQ, look what happens. Here I have unexposed resist, so I have nothing more than a mixture of resin and increasing amounts of sensitizer concentration. And what happens to my development rate? It goes down. Remember, this is a logarithmic scale, so it's going down exponentially. But if I go up to 25 or 30% by weight sensitizer mixed into the photoresist, I can make the development rate of that mixture decrease by a couple orders of magnitude. This is why we call the DNQ a dissolution inhibitor. It inhibits the dissolution of the Novolak resin. On the other hand, the carboxylic acid enhances the dissolution of the Novolak resin, so we call it a dissolution enhancer. If I look at the fully exposed resist, I take the same resist and now expose it so that all of the DNQ converts to carboxylic acid. Now I get a higher development rate than Novolak resin by itself. This fully exposed resist increases in dissolution rate by on the order of 1 order of magnitude when I get up to the highest possible concentrations. If I try to put in more than about 30% weight percent DNQ into a Novolak resin mixture, it tends to be unstable in the solvent and precipitates out. So this represents about the maximum concentration. And look at the solubility differential here between fully exposed and unexposed resists. It can be up to a factor of 1,000, the ratio of fully exposed development rate to fully unexposed development rate. So that explains how the DNQ works. Now let's try to quantify the magnitude of the effect. And we'll do that to start with by looking at the kinetics of exposure. How fast does the exposure reaction proceed? Kinetics is the study of how fast a chemical reaction proceeds, and we express the kinetics in terms of a rate. So dm dt, m is the concentration of the sensitizer, and dm dt is the rate at which sensitizer disappears upon exposure. As such, it will have a negative value because sensitizer is going away. And we say that this rate is first order if the rate is proportional to the concentration of the material reacting to the first power. And that's what we have here. For our photoresists, the kinetics are first order. There are some materials that have second order kinetics, but all of the photoresists that we use in conventional lithography today all employ first order kinetics. It's first order in the sensitizer concentration. It's also first order in the light intensity. That is, it's proportional to the intensity of light to the first power as well. Then we turn our proportionality into an equality by throwing in a constant called the rate constant, and I'll use the letter C to represent the exposure rate constant. This is our kinetic equation. We can justify why it should be this way, but eventually we'll have to experimentally verify that in fact our materials expose in this manner, and that has been experimentally verified. So what can we do with that kinetic equation? Well, if the intensity is constant with time, we can integrate. Simply integrate by putting the m on the other side of the equation, dividing by m, take the dt, put it over on this side of the equation, integrate both sides of the equation, and we find an exponential result. M, the concentration of sensitizer as it changes with exposure time, is equal to m0, the initial or unexposed sensitizer concentration, times e to the minus CIT. We'll often rearrange that very slightly and define a relative sensitizer concentration, little m. Little m will go between 0 and 1. So 1 for a completely unexposed material, going down to 0 for a completely exposed material. And the thing that determines the amount of chemical change is I times T, called the exposure dose or the exposure energy. We use those two terms interchangeably. So if I were to plot that equation, little m starts at 1 for completely unexposed material, and if I were to give it an infinite dose, it would eventually level off at 0 in this classic exponential curve. I times T is the exposure dose or energy. It has units of joules, or more commonly millijoules, per unit area. So it's really a dose per unit area or an energy per unit area, but we kind of always assume we're normalizing the energy by the area that we're exposing over. So the exposure dose per unit area is what we call the dose. Millijoules per square centimeter is the most common units. Therefore, C must have units of inverse dose, so centimeters squared per millijoule, and here's a typical value for the rate constant C. This brings up an interesting topic called reciprocity. Reciprocity always occurs for resist materials that undergo first-order kinetics. And what is reciprocity? It's very simple. When I expose resist, it's neither the light intensity nor the exposure time that really matter. The only thing that really matters is the product of the two, or the exposure dose. Only the dose affects the amount of chemical change. For any system that exhibits reciprocity, I could double the light intensity, cut the exposure time in half, and get the exact same result. Only the product matters. If I cut the light intensity by 3 but increase the exposure time by a factor of 3, I would get the same result. We use this phenomenon in the world of photography as well, where we change shutter speeds and aperture stops that result in a change both in the exposure time and the intensity of light hitting the film. And because of reciprocity, as long as I keep the product constant, I can get the right exposure on my film. Same thing is true for photoresists. And this is important in lithography because it affects how we control the exposure process. Mercury arc lamps, for example, decrease in intensity with time. The quartz tube that the arc lamp is contained within vitrifies and becomes less transparent. Also, the metal electrodes over which the arc passes, between which the arc passes, begins to sublimate and coat the inside of the mercury arc lamp, and as a result the intensity decreases with time as the lamp ages. It can get down to 80–70% of its initial intensity before we chuck the lamp and put a new one in. But that's okay, we simply increase the exposure time in proportion to the decrease in intensity and we'll get the same result. In other words, we integrate dose. And as long as the dose is constant, we have controlled our lithographic results. Excimer lasers have pulsed power output. Each pulse is only about 20 nanoseconds long, and we typically use on the order of 100 pulses to expose the photoresist. But our ability to control the energy of each pulse is not so great. We get maybe 1 to 3% pulse-to-pulse energy variations. But I can live with that as long as I can measure the energy in each pulse and integrate the total amount of energy and cut off the exposure when I've reached the right dose. So in both of these cases, we use reciprocity to allow us to more effectively control the lithographic outcomes. All right, what have we learned in Lecture 49? As always, you should be able to quickly and easily answer these questions. If not, you need to go back and review some of the material. What are the two main tasks of a photoresist? Of course, there are more than just two. You might also think, can I recall how many of the other tasks can I recall? But first, what are the two main tasks of a photoresist? What are the three major components of a photoresist? Name three types of photoresists that have been used in semiconductor manufacturing throughout its history. How does DNQ exposure affect the solubility of a photoresist in developer? What is the mechanism? What's the means by which exposure of the DNQ changes the solubility of the photoresist? And finally, what is reciprocity? Next time we'll talk a little bit more about exposure and exposure kinetics, and then we'll move on to chemically amplified photoresists.